So in this talk, I'm going to describe how you represent a linear transformation by a matrix. But let me start by just reviewing something about bases of vector spaces. So let's recall a basis for a vector space V is a set that's called B, E1 up to En, a basis of vectors, such that, first of all, V generates the vector space V. That means that every vector in V is a linear combination of vectors in the basis B. And second, B is a linearly independent set of vectors. And it follows, therefore, that the dimension of V is equal to the number of vectors in B, because the dimension of a vector space is the number of elements in a basis. And the fundamental theorem of linear algebra says that no matter what basis you choose for a vector space, all bases have the same number of elements. And a consequence of this is not only that every vector in the vector space is a linear combination of vectors in the basis, but every vector in V is a unique linear combination of basis vectors. So what that means is that if V is a vector in the vector space V, and let's say our basis is E1 up to En, if V is some linear combination x1, E1 up to xn, En, so that's V is a linear combination of E1 up to En, and also V is a linear combination, another linear combination. So it's the same basis vectors, but the coordinates here, the coordinates are xi, and here the coordinates are yi. Then, in fact, they have to be exactly the same. x1 equals y1, x2 equals y2, and so forth. Xn equals yn. So this is what it means to say that a vector is a unique linear combination of the vectors in V. When you write V as a linear combination of the vectors in the basis, there's a one and only one way to choose the coordinates. And we have what is called the coordinate vector of V with respect to the basis. V, I put it in square brackets, E means the basis. These are the coordinates, x1, x2, up to x sub n. And if you have different bases for a vector space, they will have different coordinate vectors. So let's look at an example of this, several examples. First of all, in Rn, what is the standard basis? This is the one everyone knows. It has to be n vectors. So E1 is the vector 1, 0, 0, 0. E2 has has 1 in a 0th place and everywhere else. E3 is 0, 0, 1, and so forth, and so forth. So this is the standard basis for Rn. So for example, in R2, the standard basis, every basis has two vectors in it because R2 is two-dimensional. So the standard basis script E consists of the vectors E1, which is 1, 0, and E2 is 0, 1. In R3, the standard basis is E1 is 1, 0, 0. E2 is 0, 1, 0. and E3 is 0, 0, 1. So that's the standard basis in R2, and this is the standard basis in R3. But there are many other bases. For example, in R2, suppose we let F consist of the following two vectors. Say F1 is the vector 2, 3, and F2 is the vector 1, 2. So I claim this is a basis. First, we have to prove that this is, so claim F is a basis for R2. Why is that? Well, suppose x1, or let's use x and y. Suppose x 2, 3 plus y 1, 2 is the 0 vector. That's the same as saying this is 2x plus y 3x plus 2y. So for this to be the 0 vector, means x and y satisfy the equations 2x plus y equals 0, 3x plus 2y equals 0. What are the solutions of that? Well, if you subtract the first equation from the second, you get x plus y equals 0. So y is minus x. You plug that into the first equation, 2x plus y is 2x, and y is minus x is x equals 0. So x is 0, and y is 0. So the only linear combination of the vectors 2, 3, and 1, 2 that gives you the 0 vector is the trivial linear combination with x and y both 0, which means these two vectors are linearly independent. And they have to be a basis because R2 has dimension 2, so any two linearly independent vectors form a basis. So suppose we take the vector xy in R2, and I want to compute the coordinate vector. Let me call this AB. Suppose I take a vector AB in R2, and I want to compute the coordinate vector for AB with respect to this new basis F. So what that means is so if this coordinate vector is xy, this means AB is x times F1 plus y times F2. These are the coordinates of this vector AB with respect to the basis F. That means the linear combination F1, xF1 plus yF2 has to equal AB. What are x and y? So again, everything comes down to solving linear equations. So this is AB equals x times F1. F1 is the vector 2, 3. And y times F2, which is the vector 1, 2. So this is the vector 2x plus y, 3x plus 2y. So to find the coordinate vector of AB with respect to the new basis, we have to solve the linear equations 2x plus y equals A, 3x plus 2y equals B. So again, we can solve it any way we like. This is just high school algebra. So for example, if I subtract the first equation from the second, so my first equation is 2x plus y equals A. If I subtract the first equation from the second, I get x plus y equals b minus a. And again, if I subtract the second equation from the first, I get x equals, 2x minus x is x, y minus y is y, a minus b minus a is 2a minus b. So that says x has to equal 2a minus b, and this says y equals b minus a minus x. which is b minus a minus 2a minus b, which is b plus b is 2b, minus a minus 2a is minus 3a. So if this is correct, the coordinate vector for AB with respect to the new basis f is 2a minus b, 2b minus 3a. So is this correct? Well, I mean, I always make mistakes, so I always check. So let's check. If I take 2a minus b times the vector f1 plus 2b minus 3a times the vector f2, let's see, what is that? That's 2a minus b times the vector 2, 3 plus 2b minus 3a times the vector f2, which is 1, 2. So let's see. This vector is 2 times 2a minus b, 3 times 2a minus b. And this is 2b minus 3a, 2 times 2b minus 3a. So what is that? This is 4a minus 2b plus 2b minus 3a. And this is 6a minus 3b plus 4b minus 6a. So here everything cancels. I'm left with 1a and 1b. So this is correct. This linear combination of f1 and f2 gives me the vector AB. So it's very important to understand, if you have a basis for a vector space, how to calculate the coordinate vector of a vector with respect to that basis. Okay, now let's go back to linear transformations. So suppose T from V to W is a linear transformation. So suppose that E, which is the vectors, is a sequence of vectors E1 up to En, is a basis for V. Let's say dimension of V is equal to N, and dimension of W is equal to M. So a basis for V will have N elements, and a basis for F will have, this is a basis for W, this will have M elements. And I'm going to show that every linear transformation T with respect to a basis is in fact a matrix. So we saw matrices in connection with solving linear equations, but now we're going to see how, if you take a linear transformation from one finite dimensional vector space to another, if you fix a basis for each vector space, the linear transformation is just a matrix. It's going to be an M by N matrix, where N is the dimension of the domain V of your linear transformation, and M is the dimension of the range of the linear transformation. So let me show how to do this. And this is really all we need to know about matrices and linear transformations in this course. But it is a basic fact that you really do need to know. So suppose we let V, again, T is a linear transformation from V to W. And we have E, which is the sequence of vectors E1 up to En. This is a basis for V. And F, which is a sequence of vectors F1 up to Fm, is a basis for W. So suppose we take V in the vector space V, and if we say that the coordinate vector of v with respect to E is x1, x2 down to x sub n, what this means is, that v is x1 e1 plus x2 e2 up to xn en. That's what it means to say this is the coordinate vector of v with respect to the basis E. So what is T of v? T of v is T of x1 e1 plus x2 e2 up to xn en. And because T is linear, this is x1 T of e1 plus x2 T of e2 up to xn T of en. Which says what? It says the linear transformation T, it has to be defined for every vector v in the vector space V, and there are infinitely many vectors v, but this is completely determined by, if you look at this formula, once you know T of v1, T of v2 up to T of en, once you know those n specific vectors, you can calculate T of v for any vector v. It's completely determined by T of e1, T of e2, and so forth, up to T of en. So for any j between 1 and n, so T of ej is a vector in W, right? Because T maps vectors in V to vectors in W. And suppose we let T of ej, that the coordinate vector for T of ej with respect to the basis F for W be, let's say, y1, y2 down to y sub m. Right? So what that means is that, sorry, that's not what I want to say. Not bad, but it's not what I want to say. Let me do this in 2 steps. So if T of ej is in W, then that implies that T of ej is some linear combination of the basis vectors for W, F1 plus F2 up to F sub m. So some linear combination, let's say this is A1J F1, A2J F2, and so forth, up to AMJ FM. So T of ej is a linear combination of the vectors in W. So the coordinate vector for T of ej with respect to the basis F will be A1J, A2J, down to AMJ. So what we have is the following. Let me just repeat this new page. I have T from V to W. I have E, E1 up to En. This is a basis for V. I have F, which is F1 up to Fm, which is the basis for W. And for each vector, Ej between 1 and n, T of Ej is summation Aij F sub I goes from 1 up to m. Another way of saying that is that the coordinate vector of T of Ej with respect to the basis F is the column vector A1J, A2J, down to AMJ. So suppose we have a vector V in V, and the coordinate vector for V with respect to E is x1, x2 down to x sub n. which is the same as saying V is the sum x1 e1 plus x2 e2 up to xn en. Or if you like, summation xj ej, j goes from 1 up to n. So what is T of V? T of V is T of the sum xj ej. J goes from 1 up to n. Ej is a vector in the basis, xj is a scalar. Because T is a linear transformation, this is summation. J goes from 1 up to n, xj, T of ej. This is summation. J goes from 1 up to n, xj. And T of ej is this linear combination of the f vectors. So this is summation. I goes from 1 up to m, aij, fi. If I interchange summations, I get summation I goes from 1 up to m, summation j goes from 1 up to n, aij xj times the vector fi. So T of V is this linear combination of the basis vectors f. So T of V, the coordinate vector for that, with respect to the basis f, is the vector whose ith coordinate is this sum. Summation j goes from 1 up to n. This should be an I here. No, sorry, that's right. J. aij, a. So this is when I equals 1. A1j xj down to summation j goes from 1 up to n. A m j xj. What is that? Well, if you remember matrix multiplication, that's exactly what you get. You take the vector x1, x2 down to x of n, and you multiply it by the matrix a11, a12 up to a1n, a21, a22 up to a2n, down to am1, am2, amn. And in fact, so this is these columns, they're n columns, and they're exactly the coefficient vectors for the linear transformation T applied to the basis vector ej. So this shows, this is a proof and actually a construction, that if you have a linear transformation on finite dimensional vector spaces, and if you choose or are given bases for the vector space, then you can represent the linear transformation always by a matrix. So let's look at some examples of that. Let's take a simple example. Suppose we take V and W to just be R2. As we take as our bases, the same bases, the standard basis, 1, 0, and 0, 1. And suppose T from R2 to R2 is the linear transformation defined by, let's say, T of xy equals 3x minus 7y, 5x plus 4y. And so this is a linear transformation. One can check directly that this is a linear transformation. What is the basis? So I have to compute T of E1 and T of E2. T of E1 is T applied to the vector 1, 0. When you apply this to the vector 1, 0, you get 3, 5. T of E2 is T applied to the vector 0, 1. When you let x equal 0 and y equal 1, you get -7, 4. So the matrix for T, I'll just write it like this, I'll call it A, with respect to these two bases, from E to E, or E to F. This is the first column. This is the second column. So this linear transformation is defined by a matrix. And of course, you can just check, because if you take the matrix 3 minus 7, 5, 4, and apply to the vector xy, this is exactly what you get. So when you have a linear transformation defined like this, with respect to the standard bases for both the domain and the range, the matrix is really very easy to calculate. So let's make it more interesting, if you like. Suppose we take the same linear transformation from R2 to R2. And instead of the standard basis, we take E and F in this case. Well, let's take the basis we were looking at a few minutes ago, which was two, 3, and 1, 2. So E1 and E2, let's call it F1. F1 is the vector 2, 3. F2 is the vector 1, 2. And let's compute the matrix for T with respect to this basis, 2, 3, 1, 2. So this is going to take a little bit more work, but it's good. It's a very, very good exercise. We will do it. Okay, so I have to calculate, or I have to compute T of the vector F1, the coordinate vector with respect to the basis F, and T of F2, the coordinate vector of that with respect to the basis F. So this is a little bit of work, but we'll do it. So T of F1, what is F1? F1 is the vector 2, 3. So, and T is 3x minus 7y, 5x plus 4y. So T of 2, 3, this is 3 times 2 minus 7 times 3, 5 times 2 plus 4 times 3. So this is 6 minus 21, I think is minus 15, and 10 plus 12 is 22. But I have to write this as a linear combination of F1 and F2. I have to write this as some linear combination x times 2, 3 plus y times 1, 2. How do I do that? Fortunately, I already did it. So at the beginning of this lecture, if I took the vector AB and I wanted to write it with respect to the basis F, the coordinate vector was 2a minus b, 2b minus 3a. So let me just jot that down over here. If I take any vector AB in R2, the coordinate vector with respect to F is 2a minus b, 2b minus 3a. So the coordinate vector of 2, 3 with respect to the basis of t of 2, 3, that's minus 15, 22. With respect to this basis is what? So a is minus 15, and b is 22. So this is 2 times a minus b, which is 22, which is minus 30 is minus 52, and 2b, 2 times 22, minus 3 times minus 15, that's 44 plus 45, 89. That's what t of 2, 3 is, if this is correct. And what is t of f2? T of f2, which is t of the vector 1, 2, is going to be 2 times 1. Oops, sorry. What is t of 1, 2? 3x minus 7y, that's 3 times 1 minus 7 times 2, 5x plus 4y, 5 times 1 plus 4 times 2. This is 3 minus 14 is minus 11. 5 plus 8 is 13. So the coordinate vector for this, with respect to, I really should say, what is the coordinate vector for this? It's the coordinate vector here. It's equal to this. And the coordinate vector with respect to the basis f for minus 11, 13 is 2a minus 22 minus b, 2b minus 3a. So this looks like minus 35, 59. So I'm curious about this. We'll see in a minute. I'm going to check. So again, we have t of xy is the linear transformation 3x minus 7y, 5x plus 4y. And my basis f for R2 is the vector f1 is 2, 3, f2 is 1, 2. And I think I calculated that t of f1, the coordinate vector for that, is minus 52, 89. And the coordinate vector for f2 with respect to the basis f is minus 35, 54. Which means that the matrix for t with respect to the basis f is going to be minus 52, 89 minus 35, 54. That is evidently a matrix. Dubious, I am rather dubious that I do make any arithmetical mistakes since I was squeezing the writing into a small place. So I'm actually going to double check everything. So t of the vector 2, 3, 2, 3, 6 minus 21 is minus 15. 2, 3 is 22. And t of the vector 1, 2 is 1, 2 is minus 11. 1, 2 is 13. And I had calculated that the coordinate vector for t of 2, 3 which is the coordinate vector for minus 1522 with respect to the basis f, was minus 5289. Okay, let me just check. If I take minus 52 f1 plus 89 f2, this is minus 52, f1 is 23, plus 89 times f2, which is 1, 2. So this is minus 104 plus 89 minus 156 plus 178. This is minus 15. 156, 56. If I get 22 here. Oh, that's right. 22. That's exactly correct. So this is correct. And T of 1, 2, the coordinate vector for that, which is the coordinate vector for minus 11, 13, the way I calculated it, was minus 35, 54. So let me check that. Minus 35 f1 plus 54 f2 is minus 35 times the vector 2, 3 plus 59 times the vector 1, 2. This is minus 70 plus 105 plus 59, 118. So minus 105. So 50 minus 59 is minus 11, and 118 minus 105 is 13, and this also checks perfectly. Okay. So that means that the matrix for A, matrix A, for my linear transformation with respect to the basis F is minus 5289 minus 3559. That's what it is. Can't argue with success. So somehow I managed to do all those calculations without making any arithmetical error. All right, so there are several homework problems where you have to compute the matrix for a linear transformation with respect to a basis. And it's a tiny bit of work, but it's important to be able to do it and do it correctly. And check what you've done when you're done. Now, I haven't given many examples of linear transformations, but in R2, two very classical linear transformations are rotation by theta radians around the origin and reflection of a vector through a line that goes through the origin. So what's an example of a rotation by theta? Suppose we let theta, for example, be pi over 4 radians. So if you take any vector, right here you take this vector, take the circle. If you rotate this vector by pi over 4 radians at 45 degrees, this vector ends up over there. You take this vector and you rotate it by pi over 4 radians, it ends up over there. If you take this vector and you rotate it by pi over 4 radians, it ends up about over here. This angle is pi over 4. This is pi over 4. This is pi over 4. So you take any vector in the plane, you rotate it around the origin by theta radians. So this is V, and this is r theta of V. We map this vector to this vector. And this computes the matrix. This is the matrix for the rotation with respect to the standard basis. The standard basis is E1 is 1, 0, and E2 is 0, 1. So for this, you just have to remember some high school geometry. Here, let's take the unit circle. So this is 1, 0, 0, 1, minus 1, 0, 0, minus 1. It's just a circle of radius 1. This is the vector E1. If I rotate it by an angle theta, I get r theta of E1. It's right over here. What are the coordinates of this vector? Well, hopefully you remember, because you've seen it in pre-calculus and calculus. Coordinates of this vector are this over 1, this over 1. That's just cosine. This is cosine theta, sine theta. So r theta, rotation of the vector 1, 0, by an angle theta in the counterclockwise or positive direction, gives the vector cosine theta, sine theta. You take the vector 0, 1, and you rotate it by an angle theta. What are the coordinates of r theta of 0, 1? Well, the x coordinate, which is negative in this case, this over 1, that's the sine of theta. This is minus sine of theta. And the y coordinate is the cosine of theta. So the matrix for a rotation by an angle theta is cosine theta, sine theta, minus sine theta, cosine theta. So for example, if you take theta equal to pi over 4, what is the matrix for rotation by pi over 4? Cosine pi over 4, sine pi over 4, minus sine of pi over 4, cosine pi over 4. You're expected to know sines and cosines of things like pi over 3, pi over 4, pi over 6, pi over 2. This is 1 over root 2, 1 over root 2, minus 1 over root 2, 1 over root 2. That's the matrix for a rotation by angle pi over 4. Suppose we had rotation by pi over 2. What is r pi over 2? I mean, that's easy to see what happens. You rotate 1, 0 by 90 degrees or pi over 2, you get to 0, 1. You rotate 0, 1 by 90 degrees or pi over 2, you get to minus 1, 0. So the matrix for this is 0, 1, minus 1, 0. And again, it's very important to remember, for any rotation theta around the origin, the matrix with respect to the standard basis is cosine theta, sine theta, minus sine theta, cosine theta. Okay. So that's one very traditional geometric transformation in the plane. You just rotate around the origin. And in fact, there's a nice calculation you can do, because suppose you rotate by 2 angles. Suppose you rotate by an angle theta 1. And then you rotate by an angle of theta 2. And you know geometrically this should be the same. It's just a rotation by theta 2 plus theta 1. And let's just prove geometrically or prove algebraically this is correct. So r theta 2, I'm going to write down the matrices, and r theta 1, this is cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, times the matrix cosine theta 2, sine theta 2, minus sine theta 2, cosine theta 2. When I multiply, I get cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2. Here I get sine theta 1, cosine theta 2, plus cosine theta 1, sine theta 2. Here in the first row, second column coordinate, I get minus cosine theta 1, sine theta 2, minus sine theta 1, cosine theta 2, or it's minus, if I have minus that, minus this. And then second row, second column coordinate, minus sine theta 1, sine theta 2, plus cosine theta 1, cosine theta 2. And now you have to remember the addition formulas for the sine and the cosine. This is exactly the cosine of theta 1 plus theta 2, and this is exactly the sine of theta 1 plus theta 2. And this is exactly minus the sine of theta 1 plus theta 2. And this is exactly the cosine of theta 1 plus theta 2. And this is the formula for the matrix of rotation by theta 1 plus theta 2. So it's very beautiful to see that the addition formula for the sine and the cosine, which are standard things in trig, which you have to have had in, certainly in pre-calculus, come up very nicely here in linear algebra. So this is a description of the rotation about the origin by an angle theta. Now, the second very nice geometrical linear transformation occurs when you have a line through the origin. And the line through the origin, let's say, is completely determined by the angle alpha the line makes with respect to the positive x-axis. And your rotation, your map is the following. You take a vector v, draw the perpendicular to the line, and continue the same distance on the other side. So this is, I'll call it S of v. You reflect the line, the vector through the line. And so, for example, if you have this vector here, you draw the perpendicular, go the same distance in the opposite direction. So this would be S alpha of v. Alpha is just going to denote this angle, which this angle completely determines the line, whether it's positive or negative. So this is reflection through the line. I'll call it L alpha. It's the line that makes an angle alpha with respect to the x-axis. So let's see if we can figure out what is the matrix for S alpha, reflection through the line alpha. So the easiest way to figure out the coordinates or the matrix for reflection through the line alpha might be to use polar coordinates. So let's say this is the angle alpha. Look at that. So L alpha is the line. And we take a vector v. So the rectangular coordinates are x, y, but for the polar coordinates, you take the distance r of the vector to the origin and the angle theta that the vector makes with the positive x-axis. So the vector v in polar coordinates is distance r from the origin and makes an angle theta with respect to the positive x-axis, which means that this angle, so this is alpha, this is theta, this is alpha minus theta. Now, when I reflect this vector v through the line, so this is S alpha of v, I have this right triangle. This is the same in both. This distance is the same. So these are congruent right triangles. So if this angle is alpha minus theta, this angle is alpha minus theta. So the angle, so it had been that v made an angle theta with respect to the positive x-axis, but now this vector makes an angle of alpha plus alpha minus theta. So this angle is now 2 alpha minus theta. But these are congruent triangles, so this distance r is the same as this distance. So for this vector, the polar coordinates are r and 2 alpha minus theta. Now, let me just remind you that you have a vector r, a vector v, and this is r, and this angle is, let's say, theta. The coordinates of this vector are r cosine theta, r sine theta. This distance is r cosine theta. This vertical distance is r sine theta. So let's just recalculate. So I start with the vector v with coordinates x, y, and it gets sent to S alpha of v with coordinates, let's say, x prime, y prime. But what is the relationship between x and x prime and y prime? So x is r cosine theta, y is r sine theta. X prime, r is the same, but the angle is now 2 alpha minus theta. X prime is r times the cosine of 2 alpha minus theta. Y prime is r times the sine of 2 alpha minus theta. So how can I express x prime and y prime in terms of x and y? Well, again, I'll use the addition formula for the cosine and the addition formula for the sine. So x prime is r times cosine 2 alpha cosine theta minus sine of 2 alpha sine of minus theta, which is plus the sine of theta. What is that? R cosine theta is x. So this is cosine 2 alpha x. R sine theta is y. So that's plus sine is plus. So, R cosine theta is x. So this is x times cosine of 2 alpha. R sine theta is y. So this is sine of 2 alpha y. And y prime is r times the sine of 2 alpha minus theta. That's sine of 2 alpha sine of minus theta, which is minus sine theta, plus cosine of 2 alpha cosine of minus theta, which is the same as cosine of theta. So I have r sine theta, I have minus sine 2 alpha times y plus cosine of 2 alpha times r cosine theta, which is x. So for reflection through the line y, well, you have the line which makes an angle alpha with respect to the positive x-axis. The slope of this line is this over this. That's the tangent of alpha. So it's y equals tangent alpha x. That's the equation of the line. It's the line that makes an angle alpha with respect to the positive x-axis. So S alpha xy is equal to minus sine 2 alpha, is equal to cosine 2 alpha x plus sine 2 alpha y cosine 2 alpha, something doesn't look right here. So x prime is x cosine of 2 alpha plus y sine of 2 alpha, and y prime is x times r sine theta is y, so minus, so y prime is r. Oh, sorry, I wrote this down wrong. That's good. Y, so y prime is r times the sine of 2 alpha minus theta. So let me use the addition formula for the sine and not for the cosine. I'm always very glad to make mistakes because it's important to make mistakes and then figure out how to find the mistake and correct it. So y prime, so this is r times sine of 2 alpha cosine of minus theta, which is the same as cosine theta, plus cosine of 2 alpha sine of minus theta, which is minus sine theta. So here I have r cosine theta, that's sine 2 alpha x, and here I have r sine theta, so that's minus cosine of 2 alpha y. So x prime, I have cosine 2 alpha x plus sine 2 alpha y. Y prime is sine of 2 alpha x minus the cosine of 2 alpha y. So this is exactly the matrix cosine of 2 alpha, sine 2 alpha, sine 2 alpha minus the cosine of 2 alpha applied to the vector xy. So the matrix for S alpha with respect to the standard basis is exactly this. So let's take an example just to calculate this of a case where we can figure out what the answer is. Suppose, let's say we take the line, the y-axis. So this angle is pi over 2. So we take the line with alpha equal to pi over 2, that's the line. And if you take a vector, xy, and you reflect it through that line, you should get the vector minus xy. So we know the answer, and let's just compute the matrix. What is the matrix for the angle pi over 2? This is cosine pi, sine pi, those two alphas, pi, sine pi, cosine pi, minus cosine pi. This is minus 1, 0, 0, 1. Let's see, if you apply this to the vector xy, you get, in fact, minus xy. Exactly what we expect to get. Let's do another nice example. Suppose we take the line y equals x. That is, alpha is pi over 4. So we take a vector xy, we reflect it through this line. What do we get? Let's see. So s pi over 4, that matrix is cosine, so 2 times pi over 4 is pi over 2. Cosine pi over 2, sine pi over 2, sine pi over 2, minus cosine pi over 2. Cosine of pi over 2 is 0, sine of pi over 2 is 1. We get the matrix 0, 1, 1, 0. You apply that to xy, it interchanges the coordinates. You get yx. And if you just look at some examples, you'll see this is 100% correct. You take the vector xy and you reflect it through this line, you get the vector yx. So these are two of the most fundamental linear transformations in the plane. And it's nice to be able to apply our theory of linear algebra and vector spaces and calculate the matrices. And there's some homework for Tuesday that involves everything I talked about in this lecture. That's it.